Good day, everyone, and welcome back to my calculus class. Today, we want to be looking into the concept of intermediate value theorem, which we can abbreviate as IVT. So, functions that are continuous over intervals of the form, that is, when we have intervals that are closed, they are closed and bounded. Um, of this form, where a and b are real numbers, they have many useful properties in mathematics. So we want to look at one of them by looking at the intermediate value theorem. So we say, let f be continuous over a closed bounded interval a comma b. That is the first condition. F must be continuous. That is, the function is continuous. F is continuous. F is continuous over a closed and bounded interval, say a comma b. If z, you can call it any, you can denote it using any alphabet, doesn't matter, or any letter in general. So if z is any real number between f of a and f of b, that is, the function value when you evaluate it at a and when you evaluate it at b. For example, on this graph, you have f of b here, you have f of a here. So if z is any number in between, then there is a number c in that closed and bounded interval such that when you evaluate your f at that c, it is going to be our z. That is all about intermediate value theorem. Let us think about it. You have a continuous function, that is, there is no break, no jump discontinuity, no removable discontinuity. It is continuous on, say, this interval a comma b. Now, you evaluate f of a, you evaluate you evaluate f at a, you evaluate f at b. And then we are saying any real number you pick in between those two y values, there will always be an x value that gives birth to that y value. That is what we are saying. Okay. Now, let us apply this theorem. The intermediate value theorem is used to verify the existence of an equation's root in a given interval, which shows whether the given function has its 0 or f of x equals to 0 within that interval. That is, we can use the intermediate value theorem to check if a function has a 0 within an interval. That is very beautiful because there are some complex situations whereby, let me give you an example. Suppose I give you something like this. F of x equals to x squared plus 5x, maybe plus 6. And I ask you, find the zeros of this, or, you know, does it have a 0? Let's say on this interval, let's say minus 3, comma, say 10. Well, even if I do not give you this, if I ask you, find a 0, that is very easy for you to find at this level. However, there are some situations, let's say we have f of x equals to x raised to power 7 plus 3x squared plus 5. And I say find the zeros. We are not really sure if the zeros even exist in the first place. So instead of going through the the rigor of finding the zero, the intermediate value theorem will help us to know if there is even a zero on a particular interval. So that is one of the usefulness of intermediate value theorem. For example, maybe you have seen functions that behave this way before. Let's say you have something like this. This function does not even pass through x-axis, so there won't be any zero. So it is important if there is a way we can find out if a zero exists in the first place. So if we know that a zero exists, then we can think on how to find that zero. That is what we are claiming. Okay, having said that, let us go into how we can use IVT. So the condition, f of x must be continuous. Like I said, it must be continuous on a closed and bounded interval, such that one of f of a or f of b is positive. One of f of a or f of b is positive, while the other is negative. That is, they have opposite signs. If that happens, f is continuous on a closed and bounded interval, f of a and f of b have opposite signs, then look at given that f of x is continuous on a closed and bounded interval, and f of a and f of b have opposite signs, then that is when we can make that claim that what? There exists a point C in that closed and bounded interval such that if you evaluate that function at that C, it is going to be zero. Okay, let us apply that here. Our question here is, show that f of x equals to x raised to power 4 minus 2x cubed plus 3x minus 21 as a zero on the interval 1, 3. Well, we observe that f of x is continuous on 1, 3. How do I know that? Since f of x is a polynomial function, is a polynomial function. Okay, so that first condition is satisfied. Our function is continuous on that closed and bounded interval. Now, the next thing we want to check is the signs. Okay, how do we do that? Then we evaluate f at the endpoint 1, so which is 1 raised to power 4 minus 2 times 1 raised to power 3 plus 3 times 1 minus 21. So this is 1 raised to power 4 minus 1 raised to power 3 is 1 times 2, that is 2. So 1 minus 2, that is negative 1. Negative 1 plus 3, that is positive 2. Positive 2 minus 21, that is negative 19, which is less than 0. F of 3 is, again, 3 raised to power 4 minus 2 times 3 raised to power 3 plus 3 times 3 minus 21. So that is 3 raised to power 4, that is 81. 3 raised to power 3, that is 9 times 2, that is 54. So you have 81 minus 54, if my calculation is correct, plus 9 minus 21. So plus 9 minus 21. If I look at this, 81 plus 9, that is 90. If I look at this 54 minus 21, that is negative 75. So definitely my answer here will be greater than 0. So they have opposite signs. I can conclude. Then, I can say, let me write it very well. I can say, therefore, by intermediate value theorem, there exists C between that 1, 3, right? Such that, yes, you can write such that like this in maths. Don't worry, it is accepted. So such that, was it? When we evaluate our f at that point C, it is going to be a 0. So that is the end of our proof. We are done. The first thing we check, our function is continuous on a, not just continuous, on a closed and bounded interval, which we are given. Then we check for the signs and we realize they have opposite signs. Then we can say by IVT, there exists a C, that is a point in that closed and bounded interval such that when you evaluate our function, at that point C, it is going to be a 0. So that is that. Let us look at another example. Show that f of x equals to x minus cosine of x as at least 1, 0. Now, for this problem, let us observe this. We do not have any interval given, but we were asked to show that that function has at least 1, 0. This means that we are at liberty to choose any closed and bounded interval where that function is continuous and see if, we have to show that there is a 0 in that interval anyway, because the problem says show that this function has at least 1, 0. So we need to carefully choose our interval. So I start. We do not have interval, so we need to look for a closed and bounded interval. So I will say let f of x be defined on, I can choose 0, pi over 2. That is between 0 and 90, 0, pi over 2. We observe, what do we observe? We observe that f of x is continuous, on 0, pi over 2. Is that true? Since or because x is a, I can call it a polynomial function, polynomial or monomial, polynomial function, and cosine is continuous. We have already proved this before in this class, and cosine is continuous on the interval. So the first step is done. X will always be defined and continuous on that interval. And cosine between 0 and 90. How do I know? It is very simple, guys. Just remember your unit cycle. You remember for cosine or something like this, in the, no, that is not beautiful. In the unit circle between 0 and 90, cosine, this is 1 comma 0, this is 0 comma 1, right? So you can see any value I pick in this first quadrant, cosine we have a value for it. So it is defined, it is continuous there. Okay, now let us check for sines. That is the next thing we need to do. Let us check for sines. So we need to compute f of 0. F of 0 is going to be 0 minus cosine of 0, which is 0 minus 1, which is negative 1, and it is less than 0. F of pi over 2 is pi over 2, that is pi over 2 minus cosine of pi over 2, which is pi over 2 minus cosine of pi over 2 is 0. So that is pi over 2, which is greater than 1. I mean, sorry, greater than 0. In this case, we see that they have opposite signs. I can just say then by the intermediate value theorem, there exists a point in that interval 0 comma pi over 2 such that if I evaluate my function at that point, it is going to be 0. So if you put this function in decimals, you plot it all on your graphing calculator, you will see that it is going to pass through the x-axis on that region 0 comma pi over 2. So the question that you may have is, how do I pick that interval? How do I know the interval that will work? It is just your ability to think fast about your unit circle, your understanding of the behavior of cosine and sine function, how they behave in the unit circle or when you graph them. So that is how you can carefully choose that. I knew that at pi over 2, cosine will be 0. And definitely it will make whatever I'm picking for this guy to be positive. And at 0, cosine is 1. And since I'm having negative here, I knew that it will make me have a negative value here. So it is as simple as that. Moving on, let us take a look at some further application. When can you apply the IVT? This is a try it for you, but let's work it together. If a function is continuous over 0, 2, and we have f evaluated at 0 to be positive, f evaluated at 2 to be positive, can we use the intermediate value theorem to conclude that f of x has no zeros within the interval 0, 2? We need to be careful with this problem. We need to be careful with this problem. So we know that f of x is continuous over 0, 2. Let me draw something. Let me make a graph. Let me make a graph. Look at this graph. Suppose this is 0, this is 2. Suppose we have something like this. This is a graph. Look at this graph. A graph can behave this way. It is continuous. 0 to 2, it is continuous. Um, so this is A, this is f of A, B, this is f of B. Now, look at this. F of 0 is greater than 0. F of 2 is also greater than 0. Our function is continuous on that interval. Now, can we use IVT to conclude that f of x has no zeros within the interval 0, 2? It turns out that this example I'm giving says otherwise. We cannot use IVT to make that conclusion. We cannot, because I have just created something here where, in fact, we have two zeros there, and it is within 0 and 2, right? So it is not enough to make that conclusion because we have that situation. What IVT tells us is that if f is continuous on that interval, they have opposite signs, then we are guaranteed that there will be a 0. If otherwise, then we need to sit back and maybe think further. We cannot conclude that, okay, there won't be a 0. So in this case, we will say, no, we cannot make such conclusion. So, because it will be very, very difficult for us, not maybe difficult, it will be very, very you know, not ideal for us to conclude that because it does not satisfy IVT, then there will not be 0. So, okay, I hope that makes sense to you guys. Oh, I hope that makes sense to you. Let us think about this. So suppose f of x is, let's say, suppose f of x equals to, let me just use equals to. Suppose f of x is equal to, say, x minus 1 squared. Observe that that function is continuous on 0, 2. It's a polynomial function. F of 0 is that is 1. F of 2, f of 2 is 1. Because 2 minus 1, that is 1. 1 squared, 1. 0 minus 1, negative 1 squared, that is 1. So we have the situation whereby f of 0 is greater than 0, f of 2 is greater than 0. So the condition is satisfied for our situation. But we can find a number 1 that is inside that 0, 1. I mean 0, 2, such that f of 1 is 0. Do you see that? If we plug in 1 here, if we plug in 1 here, so that is 1 minus 1, 0. 0 squared is 0. So you can see we cannot use IVT to make such a conclusion. So that is a concrete example there. And you can see from my graph here, I also showed you one that I can find a situation whereby I can have a 0, even though f of 0 is greater than 0 and f of 2 is greater than 0. A question you might have is, teacher, is it enough to use something like this to prove? Yes, it is enough. You don't even have to use something like this. This is enough for you to prove that you cannot use IVT in that situation. That is enough. You only need to say, consider the graph below. Consider the function. So that makes sense. Then you say f of a is greater than 0, f of b is greater than 0, but there exists a point in between such that the f evaluated at that point is 0. So I hope that makes sense to you. Moving on, let us look at this also. For f of x equals to 1 over x, f of -1 is -1, okay? And f of 1 is 1, which is greater than 0. This is less than 0, okay? Opposite signs. Can we conclude that f of x has a 0 on the interval? Well, we know that for us to be able to make that conclusion, f of x must be continuous on that interval, -1 to 1. But you can see from -1 to 1, there's a 0 in between. However, we cannot divide by 0. So we say, we observe, let's say, we observe, what do we observe? We observe that f of 0 is undefined. Undefined. That is f of x is not continuous. It's not continuous on -1, 1. So we cannot apply IVT in this situation. Okay, done. So you are at the level of math whereby it is not just you making calculations. You're trying to analyze the situation you have. So that is why you really need to have the good understanding of what is going on. So I will leave you with this to show if this function has a 0 over the interval 0, 1. That's a try it for you that I want you to show. Okay, the next thing we want to look at is the precise definition of a limit. Before now, we have been looking at the intuitive definition of a limit. It is, we consider limit from the left, limit from the right, but then we have not been able to give a precise definition of what we mean by that coming from the left, coming from the right. So now we are about to do that. Let me take you back to when we started our work on limits. We started by saying, let us pick points, 0.1 away from where our x is going to approaching. Then we say, okay, we can lower it to 0.01. We can lower it again to 0.001 to 0.0001. You remember? And then we kept seeing what is happening to the y value. The same idea we want to use now to make a precise definition. So instead of taking all this point, because then we concluded that we can talk about many points, 0.1, 0.01, 0.0001, 0.00001, because our answer will keep getting better and better and better. Now, let us quickly consider this function. F of x equals to 3x minus 6. Okay? We want to show that the limit of this function, 3x minus 6, as x goes to 5, is 9. Is that true? Yes, if we substitute, that is 15 minus 6, and that is 9. Okay, this is where I have 9. My 9 is here, 9. I can do this, and you can see that is my x is approaching that 5. Now, we can ask this question. How close to 5 does x have to be so that f of x differs from 9 by less than 0.1? That is, how close do we have to get to 5 so that the function value, that limit value, will be less than 0.1? Remember, the more we have that value closer to 9, the finer our answer becomes. And that only happens as we get closer and closer and closer to our A value here, right? To our A value here. So let's say, for example, here, let's say I'm having 0.1. So here, 0.1. Remember, from the left, from the right, 0.1. Now, it then means I can do something like this. I can do something like this. Maybe that is 0.5, but I will take it as 0.1. Then I can trace it down. Sorry, guys, that's my writing pad is not really giving me something I want. Okay, so something, you know, um, of that nature. Now, let us make some definition. I'm talking about distance. So look at this. There is a distance from this 5 to this point that I'm seeing. And there is a distance here that I'm seeing from the left and from the right. Okay? So the distance from x is, I can write it this way, right? Because I'm considering both sides. If you remember, if you have something like this, say, absolute value of x. So remember, you can write that as minus x, positive x, right? So that is why I'm considering the absolute value to help me take care of both. Okay. And also, even beyond that, you do know how we could compute distance. Okay. So absolute value of x minus 5, that is the distance. And the distance from f of x to 9 is f of x minus 9. Again, absolute value of f of x minus 9. Okay, so we need to find some number, let us call it delta, such that that function value minus 9, that is the distance between, as we are getting closer and closer on that y value, which is our target, our limit. As we are getting closer and closer to that 9, which is our limit, we want the distance to be less than 0.1 because we want it to be very, very fine, a fine answer. So we want it to be less than 0.1. And that will happen if, um, oh, sorry. Okay. So that will happen if the distance between x and 5 is less than that value delta that I can find. So I will call this place that delta. The distance between, as I'm moving, right? Between x and that 5, I will call it delta. So I want my y value, the distance from my y and my limit to be less than 0.1 because it makes it a better answer. And that will happen if the distance between x and 5 is less than some number, delta. So how do we find that delta? That is our question. Okay, so let us talk about the process. We'll start with f of x minus 9 is less than 0.1. Remember, our goal is we want to show something like this. X minus 5 is less than delta. That is what we want to get to. Okay, our f of x is, what is our f of x in this situation? 3x minus 6. Okay, 3x minus 6 minus 9 less than 0.1. We want that to happen. So that implies, I will use implies, that is 3x minus 15 is less than 0.1. And that implies that I can factor this and I will have x minus 5, right? Less than 0.1. And that implies that I can write this as absolute value of 3 times absolute value of this, less than 0.5. Now, guys, I can divide through by, okay, before I do that, this implies the absolute value of 3 is 3. So x minus 5 less than 0.1. I can divide through by 3. Then I will have that absolute value of x minus 5 is less than 0.1 divided by 3. That should be 0.033, I believe. So I will just take 0.03. Now, I've been able to arrive at something like this, which is exactly what I'm looking for. That is my goal, is to have that in that work, and I have it. And what is that now? I need to ensure that that value is less than 0.03. So now we know what our delta should be. So therefore, we need to choose delta to be 0.03. Okay, so that is just explanation. Now let us give it a formal definition. The value of 0.1 was arbitrarily chosen. Yes, I just chose 0.1. I can say I want it to be less than 0.001 because the smaller it becomes, the finer my answer is. So in general, we will use the Greek letter epsilon to denote such a positive number, to denote the distance from f of x. So come about the epsilon delta definition of limit. So that is the format, that is the precise definition of limit, the epsilon delta definition of limit. What does it say? So we say that the limit of a function f of x as x goes to a equals to a real number L If, now look at the condition, if for every epsilon greater than 0, that is for every epsilon is a very small number. We want it to be very small, but it has to be positive, right? So for every epsilon greater than 0, there exists a delta. That is our goal. We want to find that delta. In fact, we can call this guy a um, we can call this universal, and we can call this uh, existential, something like this. Something we need to look for. It has to exist, right? So another way to see this is that giving. We want it to be like that. But for it to happen, we need to find a delta that is also positive, such that if, let me break this down. Such that, for now, I will say if the distance between x and our a is less than that delta, what will happen? The distance between our function and the limit will also be less than that small number, epsilon. Well, I said I want to break this down. It is nothing serious. X minus a less than delta. This part is clear to you. That means the distance between x and a, we want it to be less than delta. Fine. The 0 here, remember, is saying x minus a is greater than 0. That is, x cannot be a. That's what we are saying. X cannot be a. And remember from our definition, even our intuitive definition, we were always saying x is not a. We are not interested in x being equal to a. We are interested in checking as x goes closer and closer and closer to a. I hope this is making sense to you. Now, I will read the definition again without stop now so that you can make sense of it. So let me go by it again. Definition. We say that the limit of a function f of x as x goes to a is a real number if, if for every epsilon greater than 0, for every small number we can get or that we pick, we want it as small as possible, there exists a delta such that if the distance between the x and our a is less than that delta, then the distance between that function and our limit should be less than epsilon. You can see epsilon as y value, delta as x value. Simple as that. Epsilon as y value, delta as x value. Okay. Now going back to our graph that we have the other time, I said here is 9. So this part that I say here, I will say, so between here and here is my epsilon. So this is 9 plus epsilon, right? And below that, here, so that will be 9 minus epsilon, right? And on the other end, if I wish I could do this to be very neat, but this writing part is not aligned that. So something I did, let me just use what I have here. Okay, so I will claim that here is 9 minus epsilon, here is 9 plus epsilon. And this end, I will claim it is, remember the distance here from 5 to that point is delta. So that is 5 minus delta. And here to this end, that would be 5 plus delta, that end. So the distance. Okay, let us look at example. Proof. using epsilon delta definition of limit, that the limits of 2x plus 1 as x goes to 1 is 3. Guys, there is a way we write proof in this situation. Now, look at what I'm going to do. I'm going to follow the definition. I will say, let's epsilon, let epsilon be greater than 0. That is the first thing you must write. If you do not write that, you lose 1 point completely. As simple as it is, you have 1 point. Let epsilon be greater than 0. It's a given, universal. You have it. Okay. We need to do what? To find, we need to find delta, which is a positive number. We need to find a delta such that whenever the distance between our x and, okay, let us label something here. I will claim this is my L. I will claim this is A. I will claim this is f of x. Okay, I hope that makes sense. Such that the distance between x and A, our A is 1, is less than that delta. Whenever this happens, then the distance between our function and the limit value is less than epsilon. We are guaranteed that will happen. So let us see if we can find that delta from f of x minus 3 less than epsilon. That implies that our f of x is 2x plus 1 minus 3 less than epsilon. Let us carefully know where we are heading to. Our goal is to find something like this, x minus 1, right? That is our goal. So let us see if we can carefully write that. So that is 2x minus 2 less than epsilon. That implies that 2 into x minus 1 less than epsilon. So that implies that I have absolute value of 2 times absolute value of x minus 1 is less than epsilon. This implies that 2 times x minus 1 is less than epsilon. And that implies that I can divide through by 2. So x minus 1 is less than epsilon over 2. I've been able to write that situation in a way that I would have that x minus 1. It is not every situation that will be this easy to, write. But for the purpose of this class, I just want to show you the epsilon delta definition of limit. So we won't be doing something much more complicated. Okay, so now that we know that, we can claim that thus we need to choose delta equals to epsilon divided by 2. That is it. So that is the value of delta. So in this case, I'm saying give me any epsilon you have, any epsilon you decide to add, maybe 0.0005. Then I will say the delta you need to choose will be 0.00005 divided by 2. That is the delta you need to choose. So that is how to prove that. Prove using epsilon delta definition of limit that this is the case. Well, again, this is L. This is our function f of x. And this is A. Okay, so again, we say let epsilon greater than 0. We must write that. So we need to find, we need to find a delta which is positive such that whenever the distance between x and our a, which is -6, is less than that delta, then the distance between our function and the limit is less than our epsilon. So let us find that delta. So from f of x minus 1 less than epsilon, that implies that our f of x is 5 plus 2 over 3x minus 1 less than epsilon. That implies that 2 over 3x plus 4 is less than epsilon. Okay, let's see if we can factor that out. That implies that 2 over 3 into, I can say this is x plus, it turns out that here has to be 6. Look at this, 2 over 3 times 6, that is 3 here 1, 3 here 2, 2 times 2, 4. So that is what I should have there. And is that our goal? Yes, that is our goal, because in this place, minus times minus is plus. So that is our goal. And it is less than epsilon. So that implies that absolute value of 2 over 3 times absolute value of x plus 6 is less than epsilon. And that implies that 2 over 3 times absolute value of x plus 6 is less than epsilon. And we can divide through by 2 over 3. That implies that x plus 6 is less than, if you divide epsilon by 2 over 3, that becomes 3 over 2 epsilon. So again, we were able to write it in the way that we want. Therefore, we need to choose a delta equals to 3 over 2 epsilon. Now, guys, please, your delta must always and must only be in terms of epsilon. It cannot have x. So when you get to a much more complicated situations, there are ways to handle such a situation. But for the purpose of this class, we'll not be considering those complicated situations. So that is what I want to teach on using precise definition of limit to prove the limit of a function. So you should go ahead and solve these two problems, and I hope you will find it easy to work with. So do not forget the epsilon delta definition of limit. So now you know the formal definition of limit. So guys, I'm going to be ending this video at this point, and I hope you enjoy it. See you in my next class. Bye-bye.